All right. Hi, I'm Allie, and I'm presenting our study of chord embeddings and the musical information they capture and their behavior in two case study applications, mixed chord prediction and artist attribute prediction. Chord embeddings are inspired by word embeddings, which are dense numeric vector representations of words utilized in most modern natural language processing or NLP applications because of the value they provide by capturing linguistic relationships. What they fully encode is still the subject of ongoing investigations, especially as new methods for creating them are introduced. However, many aspects of what they encode speak pretty clearly to our intuitions, which I'll demonstrate with these common examples. The analogy king is to man as queen is to woman can be represented mathematically in a vector space. By subtracting the vector for man from king and then adding woman, we obtain a vector whose nearest neighbor is the queen vector. This works for many analogies, such as between countries and their capital cities, and of course, many other interesting phenomena beyond analogies have also been found. As word embeddings represent words, we use chord embeddings to represent chord symbols. Embeddings are not easy to interpret, but we can use techniques to probe their relationships. If we could look at these chords, for instance, the cosine similarity between G and C is higher than that of G and F sharp. This is not surprising since G and C often occur near each other in musical passages. The subjectivity of musical semantics makes intuitions about the meaning of chord embedding relationships seemingly more challenging to derive than for word embeddings. We asked a number of musicians to describe what it means for chords to be similar, and we were met with responses along the lines of similar in what sense. This question can be raised about natural language as well. Defining the meaning of the word bank, for instance, depends on context, but you can start by listing those contexts. There's a river bank, a money bank, there's the idiomatic sense to be banking at something, etc. But our mental lexicon for the semantics of a G chord might not be as finite. People with absolute pitch might have their own intuition based on the pitches they hear. We could define it mathematically based on pitch frequencies. We could describe qualities of its sound when standing independently. We might identify ways that it functions within the context, for instance, whether it plays a particular role in a cadence. It might evoke unique sentiments from one context to another, and we may even agree on those. Even after all these ways of defining it, we can change keys, and now the G chord in G major plays the role of the D chord in D major. These definitions all have their caveats, but most importantly, context is key. In natural language, a concept that relates to the significance of context is called the distributional hypothesis, which is that words occurring in the same context tend to have similar meanings. This hypothesis is the basis for word-to-vec, the approach we use to create chord embeddings. Before further discussion, it's important to note that our data can mostly be described as Western tonal music, which is, for the most part, also our most familiar lens through which we understand musical relationships. With that said, maybe a distributional hypothesis could also be described for tonal music. So what do chord embeddings capture? We'll now look at how we create chord embeddings and the relationships we find. We obtained 89,000 chord charts from Ultimate Guitar. This is a crowdsourced site, so we see a lot of variance in the chord notations, which contributes to the power law trend observed, analogous to Zipf's law describing a similar distribution in natural language. Therefore, after normalizing, we create embeddings for chords used in at least 0.1% of the songs in the dataset, or 237 chords. We create embeddings using both variants of the word-to-vec approach, which are the continuous bag of words in Skipgram language models, which I'll call CBOW and Skipgram for short. CBOW is a feed-forward neural network that takes in a sequence of chords with one masked and tries to predict the masked chord. Throughout training, the hidden layer weights undergo updates via backpropagation, and these become our chord embeddings. Skipgram operates in almost the same way, but instead it predicts a set of context words from one word. To explore our first research question, what information do they capture, we project the embeddings in a two-dimensional space to more intuitively observe relationships between chords. We observe several relationships of interest. First, we see clearly that major chords take the shape of the circle fifths, which we help illustrate on the projection. The same shape takes place over minor chords and other qualities as well. Here we see that relative major and minors are closely represented, for instance, G and E minor and C and A minor. And lastly, we find nearness among enharmonics, and bisecting the lines connecting these enharmonics puts the sharps on the left and the flats on the right. Using these vectors derived by automatic and unsupervised means, we're able to automatically reproduce the circle of fifths, the same diagrams musicians have known for a few hundred years. Fifth intervals play significant roles in our music, and transitions between chords of this relationship are ubiquitous. Thus, word2vec learns to predict them within the presented context. Relative majors and minors appear frequently in the same context windows, especially as they commonly appear in similar places in deceptive cadences. For the case of enharmonics, it's a good time to remind ourselves of the data we're working with. The chord charts are crowdsourced and thus subject to notator preferences. In some cases, sharp and flat symbols are used inconsistently, for instance, using A flat instead of G sharp in E major context, but for the most part, symbol usage is consistent with a particular key, strengthening the observed separation of sharps and flats. How do chord embeddings operate in applications? We'll take a look at our two case studies to investigate. Our first case study is on next chord prediction. We build models to predict the next chord in a sequence, comparing ones that use chord embeddings with ones that don't. We compare them to models. Compare the models to human chord choices. For this, we draw inspiration from an NLP task called the lexical substitution task, or LEXSUB. This task is for finding lexical substitutions for a word or phrase in a given context, and substitutions made by automatic systems are evaluated in comparison to human-made substitutions. We use a similar approach to gather annotations and evaluator models, as in for both tasks, there are no right or wrong answers, and we want to account for both creative and common annotator choices. We recruited 9 annotators and asked them to rate their musical expertise. We then presented them with short chord progressions and this interface so they could test how chords sound at the end of the sequence. We measure pairwise inter-annotator agreement in 2 ways. Chord match agreement is the proportion of chord progressions in which a pair of annotators provided the same chord, averaged over all pairs of annotators. On average, almost a quarter of the chords between a pair of annotators match. However, this metric treats all chords equally. For instance, A and A7 share a number of pitches, but they're treated the same as a pair with no shared pitches. Therefore, we also compute a pitch match agreement, which is the average number of pitch matches per sample between each pair of annotators. On average, over a third of the pitches between a pair of annotators match. We also computed these metrics on subsets of annotators grouped by expertise. Interestingly, for both metrics, intermediate musicians had the highest agreement and experts had the lowest. This is something to be further explored, perhaps in a larger study, but some reason for this is that we saw the expert group using a greater variety of chords, whereas the other groups relied mainly on major and minor chords. Our automatic system uses a long short-term memory model, or LSTM, which is an RNN-type model often used for language modeling and other NLP tasks. The LSTM takes in a sequence of chords with a chord at each time step. In the embedding lookup layer, each chord is first converted to one of its 4 vector representations, which are CBOW or Skipgram embeddings, pitch representations, or random numeric initialization. The chord is passed through the LSTM layer, which has a hidden state that retains information about the sequence to predict future chords. At test time, we provided a sequence of chords, and the chord with the highest probability at the last time step is the model's prediction. I'll cover a couple of the LEXSUB metrics we used, but there are more in the paper. So first is match out of 4, and that is for each example, we calculate the fraction of annotators that included one of the model's top 4 predictions in their answer, and then average these values for all examples. Overall, the models don't differ remarkably, but we also broke this analysis down by music expertise, and we observed that all of the model's decisions match those of expert group more frequently, followed by the intermediate group, then the beginner group. To explore this further, we computed match out of 4 between each individual annotator and model and found a significant relationship between CBOW model's scores and annotator expertise. Again, the match out of 4 metric treats all mismatches equally regardless of the number of pitches shared between 2 different chords. Therefore, we account for this with the pitch match metric. This is the number of matching pitches between each individual annotator's response and the model's top prediction averaged over all samples. We observed significant correlations between pitch matches and expertise for the randomly initialized model and an even stronger correlation for the CBOW model. This chart shows a regression on annotator expertise and pitch matches with the CBOW model. Since next chord predictions correlate with expertise, significantly so for the CBOW model, this might inspire some applications of chord embeddings. For instance, they could be used for music education software, teaching music theory or composition concepts, or another could be an interactive music composition system, such as the one that represents the interface used in our annotation task, which could provide suggestions for musical directions to write or offer interesting alternative chord choices. Our second case study is to predict artist attributes from a song's chords. Composer recognition and style profiling tasks are heavily researched and are of interest to computational musicologists. These tasks relate to authorship attribution and style profiling in NLP, where word embeddings have been useful for prediction and analysis. Therefore, we wanted to explore the use of chord embeddings in the music domain. We obtained attributes about the artist from MusicBrainz, an online encyclopedia of music metadata. Among a number of attributes we extracted, we chose 3 for which we had the most data for the purpose of a large-scale approach and exploration. Those are the artist's gender, country, and whether they are a group or solo performer. To perform a simple binary classification, we take the 2 most frequent classes and downsample from the more populated classes to get an equal number of instances. The resulting task dataset contains 6,000 samples for men and women, 8,000 for UK and US, and 20,000 for group and solo artists. We start with a logistic regression as a baseline approach. We compare the use of chord embeddings with 2 other representation methods. First, we have a bag of chords approach with 2 variants. Bag of chords count represents songs by the relative frequency of each chord, and bag of chords TF-IDF represents them with term frequency inverse document frequency scores, which gives a boost to rarer chords. The second comparison method is our pitch representation model, or PR, motivated by related work and to utilize the constituents of a chord. This represents a song by a vector with 12 dimensions for each pitch in the chromatic scale with the relative frequency of each pitch. To use chord embeddings, we take all chords of the song and aggregate their vectors by max pooling, meaning at each dimension we take the value with the most extreme absolute value. Each of the models significantly outperform a random baseline, demonstrating they seem to capture signals in the data to perform the predictions. The bag of chords and embedding models significantly outperform the pitch-based models in all tasks, which might speak to the significance of the chord structures and contextual semantics. The bag of chords count and both embedding models significantly outperform the bag of chord TF-IDF model in both the artist type and gender tasks. This might mean that for artist type and gender, chord variation within a song is more significant than their general rarity in the data set, but the general rarity might be useful for distinguishing artist countries. For gender, we also observed the bag of chords counts model outperform one of the embedding models, the CBOW model. This might be due in part to the baseline's limitation that aggregating the chord embeddings loses some information captured by them. Additionally, the baseline does not account for the sequential context of the chord progression. Since word-to-vec captures relationships from context, the baseline setup might not be conducive to the embedding signals. To move beyond this limitation, we built a convolutional neural network, or CNN, based on a CNN for text classification. First, the entire song's chords are passed through an embedding lookup layer. Just like the LSTM in the prior study, the model uses one of the 4 different representation variations: CBOW, Skipgram Approach, pitch representations, or random initialization. The convolutional layer filters the chords into the feature map space, then the max pooling layer tries to get the most important features from the feature maps by taking the dimensions with max values into a new vector. Then this vector is passed through our fully connected softmax layer to produce the probability distribution over the artist's attribute classes, and the class with the highest probability is the model's prediction. So Each CNN significantly outperforms their baseline counterparts. The top performer overall is the Skipgram CNN, which significantly outperforms the non-embedding CNNs for each prediction task. As opposed to the baselines, the CNN models account for the chord progression contexts, and its setup does not involve the information loss in aggregating the chord embeddings. In this case study, we took a new approach to large-scale music style profiling by utilizing pre-trained chord embeddings. The ability of the models to detect any signals enabling the predictions suggests interesting directions for studying associations between chord usage and artist attributes. For instance, our observations led us to further investigate chord usage variance across attribute classes, such as for gender shown here. The results of our investigation signify that various forms of chord representations offer different benefits depending on problem setups and model architectures. In both case studies, we observed different behaviors from the CBOW and Skipgram embeddings. Some of these wouldn't be noticed if, for instance, we had not performed any comparison between human chord choices and only relied on quantitative metrics such as language model perplexities, which we report in the paper. Some studies in NLP have attempted to understand the functional differences of the models and advantages and disadvantages of the word-to-vec variance in natural language tasks. For instance, some have suggested that Skipgram captures better representations of rare words, while CBOW trains faster and yields better representations of more frequent words. However, these insights might only be relevant for certain scenarios within the natural language domain. So, investigating key differences between these embedding models in musical contexts is a direction for future work. All in all, chord embeddings capture musical relationships that offer potential benefits in downstream computational music tasks and could be a valuable tool for broader music research objectives. In summary, we explored chord embeddings and relationships between their vectors to understand the musical information they capture, finding important relationships described in music theory. We conducted a small-scale study into how the representations lead to predictions comparable to progressions made by experienced musicians, and then we showed their utility for large-scale music style profiling tasks. For code, you can visit our GitHub repo and my lab's download page, and you can find out more at my website. Lastly, I want to mention my thanks to my advisors in the computer science department, Rada and Jonathan, and my advisor from the School of Music. And thank you for everyone for joining.
Thank you very much. Please, some questions. You can make the questions by chat or doing directly by. Okay, I can do a very fast question. What changes did you need to adapt the CCN for originally for language to Chord analysis?
So if I remember correctly, we had to try out different, I think we had to perform different parameter experiments, and I don't remember entirely the exact variance. So we could also, I might have to go back and look.
Okay. We have,
Okay.
I think there are another question over the chat.
Oh, yeah. So for these embeddings, the embeddings that we ultimately used for all of the analyses in this paper and studies was 200. And we experimented with a number of different dimensions and parameters. And 200 led to like the most consistent results through our experiments. So that's why we chose that. But we didn't notice like major consistent drawbacks of the embedding dimensions that we explored.